So let's start. So, okay, great. Thank you, Moini. So good morning and good afternoon, everyone. Thank you for being here today. So we are a special interest group in the area of tech in the IEEE TCC and Technical Committee on Cognitive Networks community. So our interest is in the AI and machine learning and security, but we also try to catch like a broader spectrum on the similar like TCC and community. So who are we? We are like right now we are like 4 or 5 of us are in the organizing committee. Our chair is Professor Subha. She is from Stevens Institute of Technology, and there are 4 of us as vice chairs. Professor Dola Saha from University at Albany Sunny, and myself. I'm Devashree Roy. I'm from University of Texas Arlington. Professor Hanif Rahabari, who he is from Rochester Institute of Technology, and we have Professor Moinul Hussain, who is from GMU, George Mason University. So with that, we'll just, okay, okay, yeah. So we are right now in the LinkedIn, we have more than, or like almost, I think now 500 members. This is a number I took like 2 months ago, and it's always growing. We have like we generally post our activities in our group, and you can also search. We have one website, and you can also send us email. These are our email IDs. So what earlier we did was we held a distinguished seminar series, virtual seminar series. This started during the pandemic time. So we had talks from various different established professors and scientists in the area, and that went over like 2 years almost, and all these talks are available in the SIG, our website, and also you can check them out in the YouTube channel. Now like 3-4 months ago, we started this new initiative where you are all in today. So this is we call Rising Star Symposium series. So this series is like an opportunity for the senior PhD candidates and the postdocs to present their work to the broader audience. And so here our intention is to foster more mentorship and like employment opportunity. So eventually we encourage the speakers to prepare their talk in like a job talk format, 45 minutes, no more than 45 minutes, and try to interactively engage with the broader participants, broader audience. So with that idea and then with that theme, we already had like 3 talks, and today is our 4th one. So we heard from Chiai, she was from MIT, then Nadia was from NACE here, and Mohammed Saidur was from RIT. So today we have our speaker is actually the first one who is from the other side of Atlantic. So that's what we are excited about. And before I go to the details of the speaker, so it's a few logistics of the talk. So we are requesting everyone to be muted on the entry, but if you have any question, please feel free to put them in the chat box. We'll ask I and Moinul are the moderators, so we'll ask those things at the end, or if they're needed, we can ask them in the middle as well. So about the our speaker today, Mr. Changgang Zheng, he is a final year DPhil, like PhD student in the University of Oxford, UK. And he is research assistant with the Data UESTC Data Mining Lab, and his research interests include networking, in-network computing, and machine learning. So thank you, Changgang, for accepting our invitation, and we are very excited to hear from you. So with that, I will stop sharing, and the floor is all yours. Thank you.
Thanks for the introduction. Let me share the screen. So yes. Can you see the screen? I think. Yes, thanks.
Yes. Yeah.
Hello, everyone. Today, I'd like to talk about my research related to in-network machine learning on programmable network devices. And in the past, the network devices are used to be fixed functional. So this means that everyone needs to run the same protocol to make sure the internet works. And since early the last decades, the cloud providers begin to have the requirement to run their own protocol within their data centers. So they can design their own protocol to match their own service types in order to gain better performance and earn more money. And they want to also keep their own design protocols private and do not want to share it with others. In order to meet these requirements, the network equipment becomes more and more programmable, which means that it allows users to program their own processing logic and to design their own protocols. So which means that the fixed functional devices becomes programmable network devices. And the simplified programmable packet processing pipeline is constructed by a programmable parser. And in this parser, it can be used to define what are headers used in the packet and what are these headers looks like. And then it is connected to a programmable migration pipeline. And this pipeline can be used to define the processing logic of the algorithm. And then it is connected to a programmable deparser. And this deparser can use to define what the output packet looks like. And these programmable network devices not only allow the cloud providers to define their own protocol, but also allow some of the computing algorithm to be realized on them, which becomes in-network computing. And specifically, the in-network computing refers to the execution of native host applications within the network using some standard network devices. And these standard network devices include like programmable switches, smart NICs, FPGA, or even some low-end devices like Raspberry Pi that running software switches. And in-network computing can be applied to many applications. For example, it can be used to realize some network functions and help and realize some acceleration service. For example, it can be used to accelerate the training of deep neural network and by using in-network aggregation to reduce communication overhead. And in-network computing can also be used in caching system to provide key value store and used to provide network security and realize anomaly detection in the network device. And it can be also applied in the distributed system to realize in-network consensus, and also used to accelerate database and even control of industrial robotic arms. And previous work has already shown that in-network computing can bring significant performance benefits. For example, 2 orders of magnitude in latency, 4 orders in throughput. And furthermore, it can even improve the power efficiency in the order of 3. And this means that in combined, a single switch can use to replace tens of racks of full servers. And each such switch can help to reduce 1 gigawatt hour per year of energy. And this is for a single programmable network device. And actually, machine learning is also a type of application that have a potential to be realized in this network device and to provide inference service. And specifically, this in-network machine learning refers mainly to the offload of the machine learning inference or classification service from the server to the network device, which becomes in-network machine learning inference. And the simplified in-network machine learning inference can be constructed with 3 building blocks. And the first is the feature extraction, and it mainly applies the programmable parser. And sometimes also using the first several stages in the programmable migration pipeline to do the feature extraction. And after the feature extraction, it uses the following pipeline stages to realize the inference algorithm. And after the inference algorithm, the last stage is about take action. And this action can be like simply assign a label to the packet or just drop the packet or send the packet back to the incoming port, or just define some other actions based on the requirements of the use case. A simple example of in-network machine learning is shown in the slide, and it is a support vector machine. And this algorithm can be treated as a set of polynomials, and each polynomial is represent a hyperplane and will give a vote. And for this in-network implementation of SVM, and it mainly do the feature extraction in the programmable parser, and it uses parser to extract all the required features from X1 to Xn. And then in each stage in the microaction pipeline, it used to represent a hyperplane. And each stage, it uses all features as input and output the vote of that hyperplane. And after the algorithm have all the votes, it will use an additional pipeline stage to map all the votes to the output class. And compare with general machine learning, in-network machine learning is located on the network infrastructures and runs on the device like switch ASIC, FPGA with pizza architecture, different from general machine learning that runs on local PC and servers with CPU and GPU. And this device with pizza architecture is programmed by the P4 language, and different from general machine learning is programmed by C, Python, or MATLAB. And the manner of the in-network machine learning is also different. It mainly do the offline training, which means that it trains model at the backend server, and then offload the trained model to the data plane for the online inference. And there are several benefits to realize in-network machine learning, and which can be summarized into these 3 L's. And the first L is about location. Because these devices are located inside the network, and for any user-generated data that targets for cloud processing will go through the network first. So this means that any information need to be classified has already been processed by these devices. So extending this process to include classification is a natural step. And also this device exists inside the network. So in-network machine learning, unlike other accelerators, can directly benefit from this existing device and bring no extra cost or space overhead. And the second L is about the latency. So the latency between the data generation node to the data processing node will always be higher than the latency to any network device along this data path between 2 nodes. And for every avoided hop in the data center, it can help to save hundreds of nanoseconds to microseconds of latency. And if it is in a wide area network, and this number can be in the order of milliseconds. So it can be expected that doing network machine learning close to the end user or at the edge can significantly reduce the latency. And the third L is about the load. Because these network devices are designed for high throughput packet processing and forwarding, they initially have a really high throughput and can process a packet, billions of packets per second. And no matter how we increase the end host processing ability, the rate of classification of the end host is always bounded by the data rate of their attached network device. And besides, doing network machine learning means we can do the early termination of traffic, which can dramatically reduce the amount of traffic flowing inside the network to the servers. And for example, doing anomaly detection. And if we can detect and drop the malicious traffic close to the source, then we can significantly reduce the load on both servers and the network. Well, even that we have so many benefits in doing network machine learning, realize of this network machine learning mapping on programmable network device is challenging. It's mainly because of this network device have limited resources. And for example, using Tofino speech as an example, and it have a limit mathematical operation. For example, multiplication and division operations are not supported. And it have a limit memory, only tens of megabit memory are supported. And it have limit data types. For example, floating point number is not supported. And it only supports limit stages, which is only around 10 to 20 stages, which means for loop is not supported. So what we would like to do is firstly overcome these challenges and realize the in-network machine learning algorithm, the mapping of in-network machine learning algorithms on this device. And to deal with this problem, we propose 3 mapping methodologies, and each mapping methodology can support a set of different machine learning algorithms. And in total, with these mapping methodologies, we are able to map more than 10 different machine learning algorithms on the data plan to the data plan. And each machine learning algorithm can be implemented with different variations, which means that it can be implemented with different methodology, different mapping methodology. So after we know how we realize the machine learning algorithm on this device, we still find the implementation of this mapping is still difficult. And this slide mainly shows how many lines of code that need to be realized on both data plan and control plan in order to realize these different machine learning models. And we also know that implementing of machine learning algorithm is not a one-time task. And when we do the implementation at the very beginning, we need to do the adjustment of model hyperparameters. And even the model is implemented on the target. And when the time goes, the data pattern may changes, and we need to do the model update. So this 2 figures shows that how many lines of code that need to be changed with only one hyperparameter change. And we can see that around 1/3 of codes that need to be changed. So we know that implementing and updating these in-network machine learning models are cumbersome. And in order to deal with this challenge, we propose a planter framework. And this is an automated framework, which means that after user input all the model parameters, training parameters, and mapping configurations, the framework will automatically load the dataset, train the machine learning model, and convert the trained machine learning model to the data plan and control plan codes and also table entries. And then it can even, based on the setup, to compile the model and run the model, and even auto-generate a testing script to send and receive packet to the running algorithm to do the test. And this framework also have a modular framework design, so which means that it can easily be extended and fit new use case and requirements. And for example, I am a user that want to design a new in-network machine learning mapping, and we can easily realize with adding a new machine learning related module to the framework without changing the architecture, targets, or use case related module. So this means that with the help of planter framework, the user with no machine learning background can easily apply in-network machine learning in their research and use case. And also for those users that targets on generate new mappings of machine learning model can just do not care about use case and hardware targets, and can easily apply their new mappings to all the supported devices and targets, and also use cases. And currently, this framework supports all the proposed mappings by using our proposed methodologies. And currently, you can see we support more than 10 machine learning models and 56 variations, which means each machine learning model is implemented in different methods. And it also supports several architectures and multiple targets, and more than 10 data sets and several different use cases. And with the help of this framework, we test the system performance of the in-network machine learning mappings, and we can see for all the supported model on top switch, it's able to reach full line rate, which is 6.4 terabytes per second. And the latency of all the supported model when it coexists with other network functions is still be able to reach sub-microsecond latency. And we further explore if the in-network machine learning can reach the same accuracy as it is implemented on the server with same model setup. And we can see if we select a proper mapping configuration, all the model is able to reach close or just minor accuracy loss compared to the server-based application. And these mapping configurations here in the two figures are number of use quantization bits, which is the how accurate or the intermediate result is stored in the pipeline, and the model depth is how fine-grained the feature space are sliced. So this is some mapping configurations. And Planter currently have been applied to several different use cases. For example, it is applied to anomaly detection use case to do the packet flow and even file level classification of traffic. And also it is applied to the IoT traffic classification use case, and it's being extended to support runtime model update and also combined with federated learning to preserve the privacy of each IoT gateway. And it also helped to realize an in-network Q-learning algorithm to realize load balancing. And it can also be applied in edge computing and applied in the financial use case to realize the prediction of future stock price. And it can even be applied in an e-commerce use case in its caching system to detect the bot traffic. And I would like to further talk about the anomaly detection use case in this presentation. And here mainly shows an example random forest algorithm implemented in the programmable switch based on the UNSW dataset. And the model is set up with 6 trees, depth of 4, and using 4 features as the input. And with this setup, the model requires 11 tables, 3 stages, and less than 2% of memory in the data plan of the switch. And with this small setup, we can see the model is able to reach more than 90% of F1 score and reach full line rate, which is 6.4 terabytes per second, which is already good. Well, even it is good, we want to make it better. And this here mainly shows the small, medium, and large size model that is supported on a programmable switch. But we can find there is still an inference performance gap when it compared to the baseline, which is a huge size model with hundreds of features and with tens of features and hundreds of trees that is able to run on a server. So the next step we are trying to do is to further improve the in-network machine learning inference performance. And the first thing that we propose is the hybrid deployment. And in this hybrid deployment, we still only employ a small model in the switch. Well, we learn from the heterogeneous computing, and which we would like to combine the benefit of small model on the switch and large model at the backend. Because for the small model on the switch, it can provide a really high system performance, which means a high throughput and low latency inference. Well, the inference performance is limited. But for the large model at the backend, their classification performance is really high, but with limited system performance. So what we do is we just apply a large model at the backend to assist the inference of small in-network model. And how we can decide if a packet that classified by the small model needs the assist of large model at the backend? We mainly use a classification confidence on the small model to decide. And using anomaly detection use case as an example, here when traffic comes to the network, comes to the switch, and it will firstly be classified by the small model inside the switch. And the switch, the model will not only give a classification result, but also give a confidence level of this result. And for those classified as malicious and have a high confidence, and it will be directly dropped. And for those have a low confidence, it will be forwarded to the backend for further process. And for those that classify as normal and have a high confidence, it will be forwarded to the output. And with this hybrid deployment, as shown in this slide, we can see we are able to achieve close to optimal classification result within minimum resource consumption with only employing a small model in switch. But we can reduce around more than 70% of loads on the backend servers for this data-intensive use case. Well, the hybrid deployment is able to achieve a good system inference performance. its in-network or in-switch model is still limited in scalability. And this limit scalability will also influence its inference performance of the small model and further limit the whole or influence the whole hybrid system's inference performance. So we at this stage, we're thinking about how we can further scale the in-network model. And we mainly deal with this with a distributed deployment. And firstly, we think about why we cannot deploy large in-network machine learning model in network. And one reason is because the network device have limited resources. And another important reason is because the normal network functions has already consumed a considerable amount of resources in the device. And even for some of the relatively large model is able to be standalone deployed on the device. When it coexists with other network functions, they will run out of resources and most likely fail to be deployed. And if we dive a little bit detail about this, the resource consumption of this network device, and here mainly shows 4 types of different resource consumption of a open source real router, which is real router on Tofino switch. And darkness mainly shows a percentage of consumption of that pipeline stage. And we can see for the first 8 stages, the resource are to some extent used. But for the last 4 stages, resources are totally unused. And this is for a single programmable network device. And in a network, there are usually, especially programmable network, there are multiple different programmable network devices distributed deployed inside the network. And if we can jointly use these unused resources, which means that we can further scale our in-network machine learning model and bring better inference performance. So at this stage, our goal is to realize this distributed in-network computing. And what we would like to do is, if we have a large in-network machine learning target program, then we firstly slice the program and decompose it into multiple segments, and then deploy these segments along all the data paths inside the network. However, realize this distributed in-network computing is not that easy, and it has several challenges. And the first challenge is about how we can realize this, find a deployment strategy without affecting existing or normal network functions. So this means that when packets come inside the network, no matter which path it is forward, according to the routing rules, normal routing rules, it will pass all the segments in order. And we mainly deal with this challenge with the help of our ILP-based think planner. And in this planner, we firstly define several constraints. And one constraint is about the dependency, and which means that we would like to make sure the dependency between all the segments on any path is correct. And we also have a constraint to make sure the integrity of the in-network machine learning algorithm on any path inside the network. And the last constraint showing here is about resource, and which means that the available resource on each node should be higher than all the resource consumption of the segments that deployed on that node. And these constraints can be further extended based on the requirement of the use case and can be converted as the equation shown here. And we also define objectives, objective functions to make sure the explored deployment strategy are optimized. And here mainly shows 2 commonly used objectives, which is minimum the overall resource consumption and minimum the latency. And these objective functions can also be further extended based on the requirement of the use case. And further explanation related to this ILP planner can be found in our paper. And with the help of this planner, we are able to find the deployment strategy of the distributed in-network machine learning algorithm. And after we have this strategy, the second challenge is about information sharing between nodes and segments. And one is intuitive, is how we can pass information between the nodes and segments. And the second challenge is about, for each node, how it can identify the difference between packets when it comes from different paths, and or even it is from the same path, it has the difference, and how the node can understand which features should be extracted and which segments on this node should be executed. It's the second challenge. And to deal with this challenge, we mainly deal with it with our think header design. And this header is transparent to the user, which means that when packets come inside the network, this header will automatically add it to the packet and will be used to pass information inside the network. And before the packet is sending out of the network, this header will be auto-removed from the packet. And inside this header, there are two important fields used to pass information. And one field is about intermediate features. And this is used to store all the intermediate results need to be passed between segments. And the second field is important, is named bitmaps. And this bitmaps is used to record which segments has already been executed in this packet and used to tell the node which segment, which features should be extracted and which segments on that node should be activated. And after we deal with the problem of information sharing, we also design an easy-to-use framework to streamline the process. And this thing framework mainly requires the input from two parts. And one part of the input is from the network operators. And it mainly includes something related to the network, which is the topology of the network and also the available resources on each network device. And it also requires the input from the user, which includes a large in-network machine learning algorithm with some manually add annotations. And after all this are input to the framework will auto slice the input program based on the annotations and convert this program into a DAG. And this DAG combined with the DAG of the network topology will be used in Think Planner to generate the deployment strategy. And this strategy will also be used in the framework to generate the data plan code for all the network device, programmable network device inside the network. And this programmable network device will not only contain the segments of in-network machine learning algorithms, but also contain all the required normal network functions that used on each network device. And the framework will also auto-compile the generated code and also activate a testing environment and run the generated compiled program in this environment for the test. And this is an automated framework, which means that after user input all the configurations and setups, the framework can help you to auto slice the program, generate the strategy, and generate the code for all the devices. And this framework is also a modular framework similar to Planter, which means that it can easily extend it to new use case and requirements by adding new modules. For example, if the new use case require a new planner design, and we can easily support it by adding a new planner module. And currently, this framework is publicly available, and you can find this from the GitHub. And we also evaluate our distributed deployment strategy on two topology. And one is a cloud data center topology with around 33 nodes. And another is relative larger topology, which is a wide area network topology with more than 1,000 nodes. And this British telecom network topology in reality is shown in this figure. And we test different flavors of in-network machine learning algorithms using this distributed deployment framework. And we can see for this machine learning algorithm, when they have a relative larger setup, they are able to be standalone deployed on a single network device. But when it coexists with other network functions, for most of the algorithm, they are felt to be deployed together. But with the help of our distributed deployment framework, all the algorithm is able to be deployed on both topology and on all the required data paths can have all the inference function on all the required data paths. And we also test the throughput of this distributed in-network machine learning algorithm using random forest as example. And this example random forest algorithm is sliced into 4 segments. And each segment is coexist with normal network functions. And in this case, it's real router. And we can see for all the segments, they are able to reach full line rate, which is 6.4 terabytes per second. And after this distributed deployment, we're also thinking about how we can do the continuous learning and do the swiftly mitigate of the emerging threat patterns using in-network machine learning. And I would like to mainly introduce it in an IoT traffic classification use case. And under this case, it has a requirement of do the fast detection and mitigation of the threats with changing patterns. And to deal with this challenge, we mainly propose a popular framework. And this popular framework can not only realize the in-band feature extraction and fast mitigation using in-network machine learning with the help of the planner framework, but also it can do the proactive logging of the extracted features in the data plan using digest. And these extracted features will be automatically labeled by using the unsupervised based iForest algorithm. And this labeled features will be added to the training data for the model retraining, and then it will generate the migration format of the model using planter again, and do the continuous update of this in-network model by using the shadow update during the runtime without disrupting the data plan functions. And we also prototype this popular framework on Raspberry Pi with a BMA2 software switch. And it can be also realized on a Dell IoT gateway. And we test this runtime update mechanism on 2 data sets. And it shows that this mechanism is able to gain a 30% of accuracy improvement when there is a new tag account when compared to the fixed in-network machine learning model. And after the runtime update, we further think about if we can further scale this traffic analysis system across multiple gateways and jointly learn the attack patterns across these gateways will preserve the privacy of the data coming from each gateway. And to deal with this challenge, we propose a popular framework, which combines the benefits of federated learning and in-network machine learning. And in order to gain a low latency and high throughput in-network attack detection and mitigation, Flip4 applies in-network machine learning and process the traffic inside each IoT gateway. And in order to realize the privacy to prevent the privacy leakage, the Flip4 framework applies a federated learning and keep the traffic remains local, and only the model parameters on each IoT gateway will be sent to the cloud for centralized process. But these parameters are sent with noise. And applied federated learning will not only bring the benefit of privacy preserving, but also it can help to reduce the communication overhead, because this means that the data from each IoT gateway no longer need to be sent for a centralized processor to train the model. And we also evaluated this Flip4 framework on 3 IoT gateways. And we can see the global inference performance of this federated in-network machine learning system is close to the offline learning of the algorithm. And we also evaluate the accuracy cost of one of the differential privacy, which means that how many accuracy will be cost if we add the noise to the trained model. And we can see in order to keep the privacy, we only need to sacrifice 4% of accuracy, which is acceptable. So to summarize, in order to realize the in-network machine learning mapping, we propose 3 different mapping methodologies that can support 11 different machine learning models with more than 50 different variations, and which means that each different model is implemented using different methods and can be applied or meet the requirement of different use cases. And in order to easily realize this in-network machine learning algorithm on network device and use cases, we propose a planetary framework, which is an automated and modular framework that can support different architectures and target device and use cases. And in order to further increase the inference performance of this in-network machine learning algorithm, we propose a hybrid deployment system and a distributed deployment framework. In order to realize this in-network machine learning model in the own use cases, we can easily do this by applying planetary framework, DINK framework, and hybrid deployment system by adding new modules. And currently, this framework and systems has already been adopted by many other users. And maybe you are the next one that would like to use it. And that's all for this presentation. Thanks, and I'm happy to take your questions.
So if you want, you can directly unmute yourself.
Yes, and I think I've seen a question related to Taurus.
Yes.
Yes. Yes, I've seen about Taurus, and also it's following work homunculus. And for Taurus, it's mainly applies, as for if my memory is correct, it mainly realizes its deep neural network or using MapReduce. And this MapReduce block is it's not a commercial switch ASIC, which is FPGA, something like FPGA attached to the switch ASIC. So what our design focus is mainly to realize this in-network machine learning model on the commodity switch ASIC without adding new devices to it.
So another related question. What do you think of using your stuff on a chiplet?
Using what? Sorry.
All of this machine learning inference engine that you added to, say, to Fino ASIC,
Yes.
this is what you do, right?
Yes.
You added to the actual ASIC, and instead of like Taurus, you added maybe in an external FPGA, right?
Yes. Yes. I directly added to the switch ASIC of switch.
This is, I think, your main contribution.
Yes. And it's like
yes, definitely.
Yeah.
So,
Yes.
which is really good. But I have another question. Now, people are looking for using chiplets and instead of ASICs. Use a chiplet like smaller modules, connect them together to provide the intended functionality. So, I am thinking of using a chiplet dedicated to learning or in network learning or machine learning. What do you think?
I guess
Because of Moore's law is slowing down, and one way to overcome that is using the chiplets technology. So maybe we can implement your stuff in a chiplet and other functionality that normally exist in Tofino, for example, can be in one or more chiplets. This way we can take advantage of this chiplet technology.
Okay.
Have you thought about this?
Because
you
I'm
looked
not very familiar with the chiplet.
yeah,
type.
chiplet. Have you looked at a chiplet? Chiplets, which are small chips that
Yes.
implement various functionalities that used to be in one big ASIC. You can put it in different components,
Okay.
connect them or package them in a way that can provide this function, the original function. It is a
Yes.
way really
Yes.
to
Yes.
overcome the
Definitely.
slow, because Moore's law is slowing down, and now we need to overcome this. One technology to address that is to use the chiplets.
Yes. 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 It is a solution. Yes. But uh, personally think compared to our solution, the chiplets will bring additional latency overhead and cannot provide such high throughput like LAN rate.
How do you know?
I
This is a new way to do things, and
okay.
actually, this is the trend in the industry now.
Okay.
I
So
just want to get your find your opinion, because last week, for example, we had the this year chiplet conference, and it's huge. The first one was number of attendees was not that big, but now it is huge.
okay. So only if the chip of chiplets can provide us high throughput or same throughput as Tofino switch or data center switches, programmable data center switches, and have the same latency, then it can be used to replace it. Otherwise, it's to some extent like different level of edge servers with different processing ability. I personally think about it.
No, I agree. I agree. Of course, if it doesn't have the same throughput, latency, all of these things, then
Yeah.
it's not good idea. But the whole premise of a chiplet is to provide the, the function and performance to support the same function and performance requirements of an existing ASIC, for example. This way,
Yes.
as we need to add
Happens.
more transistors, and as we add in the
Oh,
future to add more functionality and maybe improve throughput, Moore's law cannot allow us to do this. This is why we people look at the chiplets. So whatever you want to do can be done with the chiplets. The only question I
okay.
have is it does it make sense to have a dedicated chiplet for the machine learning or inference, which what you are doing now, especially with distributed in-network computing, which you described in one of your papers, the DINC,
Yes.
the DINC paper, which is a good paper actually.
Yeah, thanks. Yeah, I think definitely for chiplets, I think it do have some. It definitely it is different from in-network machine learning because in-network machine learning is always bounded by the or limited by the processing ability and resources of the switch or the network devices. And the network device, because it's originally designed for packet processing and forwarding, it cannot be as that functional or provide us that much function as other chips. So if there is a chip that can provide more functionality, definitely is a supplement or it can be used also to benefit the network machine learning.
Yes, what you are saying, we can use this chiplet for existing, not even programmable, not like Tofino, maybe an existing
Yes,
device which
yes,
might not use Tofino or programmable ASIC. We
yes.
can have this functionality in a chiplet. Yeah, that's yeah,
And also using hybrid, like we
yeah.
deploy a very small model in the switch, which means that we do not consume a large amount of resources on it. And we use a middle-sized model in chiplet chip, and then we can use a huge model at the backend server. So hierarchically drop the packets.
So you can get, for example, an intrusion detection device which currently exists as a chiplet to it to do the inference using models that may be computed using a server or something on a
Yeah,
back-end device. Yeah,
yeah,
that's a good idea. Thank
yes,
you.
yes,
Hey, Changgang Zheng,
yes.
It was a nice presentation, and I really liked the concept you developed because I worked nearly like 7 years in telco network engineer, and it was very fantastic presentation. So basically, your programmable switch are reading each packet on the network, right?
Yes.
So what do you think regarding the privacy of users? So in near future, it might be the case that privacy will be breaches, right? Users' privacy will be breaches because your every node is reading every packet of each users.
Yes, but actually, for at least for packet and flow level classification, it will not read more information than a normal network switch. Because a normal network switch also need to read this information.
But in the network, like everything has some labels, right? And the edge routers append some kind of labels on each packet, and others core routers and other routers forward those packets based on that label. Basically, routers are not reading the entire detail of the packet, right?
Yes.
So, but in your feature extraction, you are adding some kind of header based on the packet information.
It
Is
depends
that
on
correct?
the task. It depends on the task.
Okay.
Yes, I totally agree with you. For example, for the some of the use case like finance and or some other just data classification, then definitely the packet should be sent without encryption. Otherwise, we need to find some place to do the encryption, then do the network machine learning. Then it have the threat for the privacy leakage. But for the anomaly detection for the packets, it will only read the packet headers like 5 tuple or some flow level feature. So for that, I think the privacy is still there. But for the other tasks, they do have the problem of privacy leakage. I agree with you.
Thank you. Thank you. Thank you very much.
So while we are waiting for people to ask more questions, I have one. Actually, I have a few, and you kind of answered them throughout your presentation. So I have just one from a different perspective, from a business perspective. So it seems like that we need to bring the user, the ISPs, and the cloud servers all on the same page to make it work, right? To orchestrate something like this.
Yes.
So from business perspective, what do you think could be some of the challenges to bring all of them together? Because the thing is that, just to give you some intuition, what I mean by business perspective is that we are essentially converting the service or migrating the service in some cases from the cloud servers to those ISPs, to all those switching equipments, right? So there is a question of revenue and all those different kind of things. Have you ever thought about these things, what it would take to realize this from a business perspective?
I think from business perspective, the one challenge is, as you say, that there should be a organization or agency that have the control of all the network device, at least areas of network device, like some company that own their own data center, or some like British Telecom that have control of ISP. And this is a prerequisite of doing like in-network machine learning and distributed in-network machine learning, and even hybrid. And the second challenge is, so for the distributed deployment, which means that we change the data plane code, at least at the very beginning of the deployment, we change the data plane code of many of network device. And what will be the trade-off between the robustness of the network versus the performance gain of in-network machine learning is another thing that should be think about before it is realized in the real business. Because it will be a disaster if we do the distributed deployment, but we have a configuration set up wrong, then the whole network just down. Then that's a problem.
Yeah, that makes sense.
Hey Cheng, I'm here again. So I have a quick query. Like, have you tested your use cases on a live network?
What? Sorry.
Uh, did you got any chance you got any chance to taste your any of the use cases in a live network?
Uh, Actually, not. Currently, all our test is in a testing environment. But in the testing environment, we still use the hardware switch to do the test, to try to try our best to simulate the real case scenario. And I think the one that close to our reality and most complex use case is the financial market prediction use case. And it based on the financial data feeds to do the time series package feature extraction, and then use these extracted features to predict the future stock price. So it is most complex use case, I have to say.
So in that case, how much the load of that switch increases uh, using that ML model in a switch?
For the load means like the
What percentage the CPU consumption of that switch increased?
For the switch, because that switch is a hardware switch, it is designed to process. It's able to process with full line rate. So which means we not very care about the CPU on the switch because it is a dedicated switch ASIC. It's a
Okay.
dedicated switch for forwarding. So
Okay.
what we really care about is the throughput and latency. But for that case, because it do a really complex feature extraction, so it requires the recirculation, which means that it will bring the latency and throughput overhead. But this overhead is not because of the in-network machine learning model, it's because of its really complex feature extraction process.
Okay, thank you.
All right, we are almost very close to the finish line. So let's wrap up then. It's just 1 minute. So thank you again, Changgang. It has been a wonderful talk. I learned a lot of new things. This is not my research area primarily, but you did a very well job in articulating all those important topics, especially the challenges you mentioned and how did you overcome those challenges and all those things. I learned a lot personally. So again, best of luck to you for rest of your doctoral program. And I hope we will meet again somewhere else.
Yeah, thanks.
someday.
I really appreciate the chance. I'm really happy to be able to share my work with you guys.
All right. With that, so this is the end of our today's talk. Goodbye, all.
Bye.
You, bye bye.
Bye, Devashri.